All right. In this last set of 4 lectures talking about magnetic fields, we're going to discuss Faraday's law and inductance. And this is extremely important. This is actually where we're going to start bridging the gap between magnetostatics and dynamic effects, which are going to lead in the next set of lectures into Maxwell's equations. What we're going to find out is that the things that we've been talking about, Gauss's law, Ampere's law, and now Faraday's law, are actually the building blocks that lead us to Maxwell's equations in the next set of lectures. The learning objectives for this particular lecture are, first of all, to learn the principles of inductors and inductance and inductors. You've been working with inductors for 3 or 4 years now in your electronic circuits class, and you hopefully have some sort of a basic understanding of what's going on. After today's lecture, you'll understand the basic field concepts for how currents in an inductor are related to magnetic flux and how this operates as an energy storage unit. You need to be able to apply the concept of inductors and inductance in solving problems in circuit theory. And then we're going to talk about Faraday's law. Faraday's law is fundamentally related to inductors. When you drive a time-varying current through an inductor, that creates a voltage across that inductor, even if there's no loss. And that is a consequence of Faraday's law. But Faraday's law has wider implications. And so you should understand Faraday's law, and you're going to need to be able to apply it. And it's actually going to be one of the bases of Maxwell's equations that we're going to talk about next time. An inductor is basically an element that stores magnetic energy. It stores energy in the magnetic field. And it's a type of magnetic coupling that occurs when you have a current, and that current creates a magnetic field. Okay? And that magnetic field then penetrates either the same loop or a different loop. So in this particular case, I have 2 loops. Right? I have a loop of wire here that's carrying current I. I have another loop over here that's got no current in it, say. And this loop of wire carrying current I is going to give rise to a magnetic field that, of course, rotates around as shown here. So my magnetic field is going in this direction. Right? And there's a certain amount of flux. Remember, this vector quantity B is the magnetic flux density, Webers per square meter. When I integrate B over the surface area, that's going to give me a certain amount of flux. Okay? But those fields, we know they must close on themselves. We know magnetic field lines cannot begin or end because there are no magnetic point charges in problems that we're interested in. And so those field lines are also going to penetrate over here in loop 2. So I'm going to have a certain amount of flux in circuit 1 that's generated by currents flowing in circuit 1. And then I'm going to have a certain amount of flux over here in circuit 2 that's generated by currents flowing in circuit 1. And likewise, if I had current 2 flowing here, that current 2, well, let's see what we can do here. We'll use a different color to demonstrate. If I had a current flowing in this wire, okay, that current in a right-handed sense would set up magnetic fields, and those magnetic fields would look like this. And they would set up a phi2, 1. Right? That would be the flux in circuit 1 due to currents flowing in circuit 2. So that's the concept of self-inductance and mutual inductance. Mathematically, we can write down a formula which tells us that the inductance, which is usually denoted by this capital phi, is equal to the inductance L times the current I. So this is the total flux equals the inductance times the current I. And we compute that flux by integrating the flux density over the area that's encapsulated here. And so in this particular case, because we have our circuit defined by this wire, the area S that we're interested in is the area inside this loop that we're going to integrate over. And we can explicitly relate the various types of inductances as we've already discussed. So let's talk about an example. And let's try to compute the mutual inductance between an infinite wire aligned with the z-axis and a square loop. And so here's my wire. My wire is carrying current I. That current I is going to set up a circulating magnetic field. So if I have a current I flowing like this, whoops, wrong tool. If I have a current I flowing like this, that's going to set up magnetic field lines that rotate around, and those magnetic field lines are going to be into the screen over here. So I'm going to have a flux going through this loop. We know that the magnetic field, magnetic flux density in this case is given by this formula here, mu naught I over 2 pi r, right? And that's going to be in the phi direction. So the fields fall off like 1 over r, and they're phi directed. And in this particular picture, the phi hat direction is into the screen, right? So that is, that's phi hat, right? Into the plane of the screen. So when I want to compute the total flux, and this should actually say phi 1, 2, I apologize for that. So this is phi, oops, do the same thing again. This is phi 1, 2. We're going to compute this flux integral, and when I compute that flux integral, the integral is fairly straightforward. So here is my magnetic flux density. In this case, the phi hat direction is equal to the y hat direction. Right? That's just in this particular plane that is true. Right? So in this plane, phi hat equals y hat, right? Where we have our right-handed coordinate system, so y is actually pointed into the screen as well. Right? So y hat dot y hat, this dot product here, of course, is going to give me 1. I can factor out these constants, mu naught I over 2 pi, okay? And my integral is going to go in the x direction, right? So in this particular cross section, r is equal to x in this plane, so I'm going to integrate from r naught to r naught plus a. Right? The integral in the z direction gave me this constant a, and of course this is just a natural log, which you know how to do, and that is the mutual inductance. Now, it is often the case, but it is not guaranteed to be so, that the mutual inductance is reciprocal. That is, that phi 2,1 equals phi 1,2. It has to do with the types of materials that you're dealing with. If you have a non-reciprocal material, then you'll end up with not necessarily having reciprocal mutual inductances. And I'm not going to go into it in any greater detail than that. Magnetic circuits, working with magnetic fields is really a discipline of electromagnetics unto itself that we're not going to spend a lot more time talking about in this particular class. It can become important when you're dealing with rotating machines and motors and phase shifters and phased array antennas and other things, but we're going to limit our discussion of magnetics to these sorts of simple magnetic problems. Okay, the next example we're going to take a look at is a multi-turn inductor. And in a multi-turn inductor, I have something interesting that happens. What we're going to find out is that each of the turns in my inductor increases the amount of magnetic field. So the total magnetic field that I have flowing in this device is proportional to the number of turns that I have in this device. However, the flux that's created by that magnetic field penetrates the loop multiple times. First, that flux penetrates one turn, then it's going to penetrate the next turn, and then the next turn. Right? So the magnetic field, the magnetic flux density scales like the number of turns, and then the flux scales like the number of turns. So we're actually going to find out that this inductance of this device, which we call a solenoid, scales like the number of turns squared. So let's take a look at this particular geometry. When I look at it, we're going to first of all treat this inductor as being infinite. So if I have this infinite inductor, what that tells me is that I can draw a series of loops, right, that have a certain amount, I can draw a series of loops that have part of the loop inside the solenoid and part of the loop outside the solenoid. Okay. Now that loop and this loop and this loop and any other loop I choose to draw have exactly the same path integral when I apply Ampere's law. When I integrate around this circuit, B dot dl, that's going to be mu naught times the total current enclosed. And So that tells me that no matter how I choose to draw my path outside, right, the total integral around this path is going to be exactly the same. And the takeaway from that is that B outside the solenoid is equal to 0. Likewise, I can draw a series of paths inside and I can choose any particular contour that I like. And the only thing that matters, the only piece that's of any importance at all, is the portion of this integral that's in the z direction. Because this extent from this end to this end tells me how many turns of my wire are included, and that's going to be proportional to the total current that penetrates the loop. Right? So the takeaway from this is that outside, my flux density is equal to 0, and inside, my flux density is B naught in the z direction. And you'll also note that I've written this field as being constant. The field is constant because no matter where I observe on the solenoid, the problem looks exactly the same. Right? So the fields must be independent of C. Right? So I'm going to use these two pieces with Ampere's law to try to compute the value of this constant for my solenoid. So I'm going to draw a loop that's partially outside the solenoid and partially inside the solenoid. That loop is going to have extent d. I'm going to describe the solenoid by a quantity called n, and little n is the total number of turns divided by the overall length of the solenoid, which I'm going to call w, and w is this much larger length. Now, we're going to assume, for the purposes of this calculation, that the solenoid is infinite. And a finite length solenoid, we would have to modify these equations a little bit. But so long as the solenoid is very, very long compared with the cross-sectional area, this is a good approximation for the physics of the problem. And I'm going to evaluate Ampere's law around this loop. So I'm going to integrate around this loop. I'm going to integrate around in this direction, in the minus z direction outside the solenoid and the plus z direction inside the solenoid. And that's going to give me the value of the interval around the loop, right, which is equal to mu naught times the current enclosed from Ampere's law is just B naught times that length d. Or again, d is that extent there. Well, if I want to know the total current enclosed inside my loop, I take the number of turns per unit length and multiply by the length. And that means that each of these turns is going to come and is going to penetrate my loop with that current I. Right? So I've got B naught d equals mu naught NID. The d's, of course, cancel. And I'm left with the total flux, which is equal to the inductance times the current. Well, this is the flux for one turn. This line here gives me the flux for one turn. And we'll call that L prime, which is equal to mu naught times N times A. Okay? And the total flux is then going to be the flux for one turn multiplied by the number of turns. And so my total flux is going to be mu naught times the number of turns squared times the cross-sectional area of the loop. Okay? Times the overall length of the solenoid. And that's our expression there for the inductance. The last thing I'm going to discuss now is the concept of Faraday's law. And Faraday's law is one of these things that was observed experimentally and then expressed mathematically. And it has to do with what happens when I have a loop that is moving in a magnetic field. It actually turns out that Faraday's law is a little more complicated like that. It's any time I have a loop interacting with varying flux. Right? So either I can have a loop moving in a constant magnetic field, I can have a varying magnetic field in a static loop, I can have a moving loop in a varying field. Right? As this loop rotates, okay, the velocity of the wire in this loop is going to have a component parallel to the magnetic field and a component perpendicular to the magnetic field. And these red arrows show the magnitude of the component of the velocity that's perpendicular to the magnetic field. And of course, we know that the force experienced by the electrons in that wire is going to be proportional to, is going to be equal to the charge on the electrons times their velocity crossed into the B field. Right? And so as this loop rotates, I get an induced current in the loop. Right? Well, that current is going to flow, and when that current flows, the electrons are going to build up at one end, and they're going to be depleted from the other. So there's going to be a voltage at this output. Right? That current is oscillating, and so this voltage is going to oscillate as well. And so that's the basic concept behind Faraday's law. Faraday's law states that the path integral of the electric field dot dl as I move around this loop, right? So that's my path integral C. That entire path integral, which in electrostatics we said that path integral had to be equal to 0 when I integrate around a closed circuit, right? But now we're going to say that when I integrate around that closed circuit, I'm going to have an electromotive force. Right? It's like I have a battery. It's like I have a source of voltage. We can solve this problem. I have my electrons that are going to build up here, which means I'm going to have a depleted region. Sorry, I got that backwards. I'm going to have my electrons building up at one end. I'm going to have depleted electrons at the other end, so I'm going to have a voltage that's induced at this end. And we say that KVL is satisfied because I pick up a certain amount of electromotive force going around this loop, and then I represent that by a voltage at the output. Right? So when I start at this point, go around and come back, I still get my 0 because I pick up a certain amount of voltage by going through this integral, and I lose a little bit of voltage here. However, if I connect a resistor across that gap, I'll get a current that's flowing across that resistor. Right? And when I have a current flowing across that resistor, I know I'm going to have a voltage drop, and that voltage drop needs to be compensated by the electromotive force when I go around. The formula for Faraday's law tells me that this electromotive force that's induced in the wire is equal to minus d phi dt, the negative rate of change of the flux. And so as this loop rotates, at this particular orientation, there's no flux. Right? Because the magnetic field is not actually penetrating the loop. The magnetic field is to the right, the surface normal of the loop is up, so I have no magnetic flux. But as this rotates, the flux will maximal 0, minimal 0, maximal 0, and so on and so forth. And so that flux is going to be oscillating. Okay? The integral takes this form, and we end up with this expression here. I know from Stokes' theorem that I can convert this circuit integral into this integral of a curl, and I can reverse this area integral with the time derivative, and I have this expression here. Since these two integrals must be equal for any area A, I end up with this form for Faraday's law, which is actually going to be one of the Maxwell's equations. The last thing I want to talk about is this minus sign. This minus sign ends up being extremely important. It's actually a consequence of conservation of energy. This minus sign is such that the induced current will create fields that oppose the change in flux. So let's take a look at my loop here. As this loop starts to rotate to the right, the amount of flux penetrating the loop is going to be increasing. Okay? When that current flows, the current that is induced, which is shown here in purple, that is going to create a magnetic field, and the magnetic field that's created by that induced current is going to oppose. It's going to go into the loop. So the rotating loop causes the flux to increase. That increasing flux drives a current which creates a magnetic field which compensates for that. Why is that the case? Well, let's imagine what would happen if as that loop turned, the current was in the opposite direction. Well, that would tell me that as the loop turned, the current was in the opposite direction, so it had a magnetic field which increased the flux some more. So that creates more current, which increases the flux more, which creates more current, and you end up with this problem that goes out of control very quickly. And so this is the concept of an energy minimization, a conservation of energy, in the sense that the induced current is going to oppose the change in the flux. That's what's said here in words. Okay. So that brings us to an end of this lecture. This is a bit of a long one. The topics that we're going to be talking about in the tutorial for today are computation of inductance and applying Faraday's law to determine induced voltages in circuits.